Today we want to find the derivative of tan x, but we don't want to look in any tables or use memorization. We want to do it by the derivative limit definition. So if y is a function f of x, then the derivative is the limit h goes to 0 of f of x plus h minus f of x over h. And I'm going to write it like this. I will take out the 1 over h in front, and you'll see why soon. This results in some better typography, you'll see. So this is what we want to do. And if we put in our function tan, we see that we have an addition of two angles. Tan of x, like this. We have addition of two angles, and so we need some addition formulas. So we need these trig addition formulas. We need one of them, but I might as well write down a whole bunch of them. The first two of these formulas, you know them very well. They're everywhere in mathematics and physics. They're the addition rules for sine and cosine. Well, I think we're going to use that for some exercises at the end. But the one that we want is the lesser well-known tangent addition formula. And you got to be careful when this is a plus here, this is a plus over here. Let me highlight this in yellow. When that's a plus, this is a plus, but that's a minus. So we must be careful with that. So let's use this. We shall use this formula here, and we'll use it on this addition of angles here in the tangent. So we'll expand this tangent here, and we'll get rid of the addition of angles, and a lot of magic's going to happen. Okay, so I just have to write all this kind of neatly. Okay, so what we want to do here now is to put everything on a common denominator, so that's going to involve multiplying a lot of stuff. Okay, so I put everything on a common denominator. I just multiplied this thing here, this part, by the denominator and put it all in the numerator. Okay, so it looks complicated, but it's not that bad, because right off the bat we can see we're eliminating this and this, because minus tan times 1 is going to cancel out with that tangent there. And another thing to note is that the reason I pulled out this 1 over h is because if I didn't do that, I'd end up with this huge triple-decker fraction, which I don't want. So it's hard to write. So it's better to write it with the 1 over h over here. Okay, so I just simplified the numerator, and we have to be really careful. It's easy to make a mistake here. There's a minus and a minus here. So that becomes plus over here. And I think we can do a little bit more simplification. Hang on. H goes to 0, 1 over h. Let's factor out the tan of h, and we get 1 plus tan squared x over 1 minus tan x tan h. And now we're done with the trig identity stuff. Now we're ready for the next phase of the operation, and that's to use an approximation. So this is real mathematics here. We're not just playing with identities. What we're going to do now is to do some real mathematics, to look at some geometry and think about it and see behaviors of as we go toward limits. So I have a figure here, and this is part of the unit circle. So the unit circle center is at A, and this is an arc. The blue part is an arc of a unit circle. Our angle is alpha, and this arc length from C to B prime is, well, that's one thing that we're interested in studying. So S is the arc length from C to B. Well, actually, let's do it counterclockwise like this. And what can we say about this? Well, you know that arc length is radius times angle alpha, but in this case, the radius is 1. So the arc length is just alpha. Okay, let's write that. So arc length is just alpha in this case. All right, so let's put some color around that so we don't forget. And we're interested in seeing what happens when alpha becomes small. So alpha starts to go close to 0. Well, interesting phenomenon starts to happen. Look at this. B starts to become very close to B prime. And when this angle becomes small, okay, this radius goes very close on top of this x. B is almost touching B prime. So the x, okay, x goes almost to 1. It becomes approximately 1. And what about y? Well, y becomes very close to s, because when we're very small, curves look straight. You know, the approximation of a chord toward that curve is a good approximation. So y is approximately s. So this is when alpha goes to 0, we have these approximations. So now we're able to calculate trig functions. So sine of alpha is what? This is the opposite over hypotenuse. It's y over 1. And what is y? Y is approximately s over 1. And that is alpha over 1, and that's alpha. So our first victory here, when alpha goes to 0, then we have sine. Okay, let's write this nice. Sine of alpha is approximately alpha. That's very good. Okay, let's put some color around that one. Now, I really want to stress that these inequalities are extremely important. I mean, they appear absolutely everywhere in mathematics, so it's really important to know them inside out. Cos of alpha, what's that? Well, cos is adjacent over hypotenuse, but this approaches when alpha is small. When alpha is small, 1 and x are almost the same, so you get 1 over 1, and that's 1. So when alpha goes to 0, cos of alpha is approximately 1. And then finally, we can figure out tan of alpha. That's sine alpha over cos alpha. But when alpha goes to 0, well, sine alpha, this is approximately tan alpha. Sine is approximately alpha, and cos is approximately 1. So that's approximately alpha. So let us put some color around that. Cos of alpha is approximately 1 for small angle. And here, tangent alpha is approximately alpha for small angle. And this is the one that we really want. So this was the last computation that we had up here. And now let's use our approximation, because limit, h is going to 0. So h is indeed small. So if h is small, we're allowed to use these beautiful approximations that we proved above. So this is going to be limit h goes to 0, 1 over h. Well, tan h is approximately h. This stays the same. Oh, that's not an h, that's an x here. So that stays the same. Okay. And 1 minus tan x. I'll put the h in front. H times tan x. This tan h is approximately h, so that's what we get. Now I can cancel out these two infinitesimals, and I end up with this limit. Limit h goes to 0, okay, of 1 plus tan squared x over 1 minus h dot tan x. Okay, now let's think about this for a second. When h goes to 0, h is very, very small, so this tangent is going to get knocked out. That x is like a constant in this derivative definition. What we're doing is making h small, not x. So for any fixed x, this h is going to eventually make this expression 0. So when we go carry this to the limit, we end up with 1 plus tan squared x, and this is just going to be 1 in the denominator. So this is the same thing, and this becomes 1, this, because the tan x gets knocked out. So I end up with 1 plus tan x. That's very nice. We could stop there, but why stop there? Let's see what we can do with 1 plus tan x. I have here one of my favorite tools. This is the universal trigonometry diagram. Okay, this is a really cool thing, and I hope to make some videos about it. So we draw a unit circle, and the radius is 1 here. Okay, so the radius, I'll draw like highlighted, the radius is 1. We draw a tangent line here. Here's our angle. All 6 trig functions then become the lengths of these lines. Cos and sine, you know already, they're the projections on the x and y axes, but the other ones maybe you haven't seen before. The secant is the blue line here, tangent there, cotangent, cosecant. But these are very, very useful to know, because I can reason about many things concerning trigonometry using this fantastic diagram. Okay, so we want to see what can we do with 1 plus tan squared. Well, radius to tangent, that's a 90-degree angle. So I have a 1 here. I have a tangent here. So if I use Pythagoras' law, what do I get? I get, okay, let's get black. 1 squared plus that. Okay, let me show you. So it's the 1 here, and then this one, tan, okay, plus tan squared alpha equals what? Well, the hypotenuse is this here, secant. So I end up with secant squared alpha. So finally, our result, we've got it in the most compact form that we are able to get, and that's secant squared x, and we're done. It's very beautiful. I really like the tools that we used for this. Just to remind you, the tools was the addition rules, which are very handy, and then we use that beautiful approximation, the small angle approximation, and then we use the universal trig figure or diagram. It's very, very beautiful computations. It's much more beautiful when you take the time to do all of the reasoning carefully, well, you know, as we have done it here. Okay, now for your homework or for some exercises, I want you to try this. Y is sine x, find y prime. What's y prime? And do it the long way like I did it. You don't need to look anything else up, okay? You don't, because we did absolutely everything here, okay? Everything you need is here. We have the identities, we have the approximations, we have, you won't need the universal trig diagram for this, but it's, well, maybe you will need it, okay? It's up to you, you know, you'll see. So you do this, okay? And I hope you enjoyed this. And if you did, please subscribe. It's always very fun to have more subscribers, and I will make more videos. I want to make like a bunch of geometry videos, especially some deep dives into this universal diagram for trigonometry. It's be very interesting. So I hope to do that, and I will see you next time.